In this section, you will learn about the I2C protocol. This is a popular communication protocol that microcontrollers use to talk to various devices such as EEPROMs and NAVRAMs, which are both memory devices. Also ADCs and DACs, which are analog to digital converters and digital to analog converters. I/O interfaces for port expansion, and a whole array of different types of sensors. So what is a communication protocol? Whenever two intelligent pieces of silicon want to communicate information with each other, they use what's called a communication protocol. Most protocols have a master and a slave device. The master is in charge of starting and ending the communication. In the I2C protocol, the master is also responsible for sending the clock signal to the slave, in addition to starting and ending the communication. So let's talk a little bit about the history of I2C. The I2C protocol was invented in 1982 by Philips Semiconductor, which is now NXP Semiconductor. It was originally built for building control electronics with various Philips chips. The original implementation was a simple 100 kHz system that has been improved over many years. It originally supported only 7-bit addresses and was limited to a maximum of 112 devices on the bus. I2C stands for Inter-Integrated Circuit Communication. Since 2006, no licensing fees are required to implement the I2C protocol, and you will see a bunch of silicon manufacturers like ST, Microchip, and Atmel using it in their devices. There is, however, a fee charged by NXP for reserving a spot in the master address list, which they own and maintain. This address is then hardwired into the device when it is manufactured to ensure that there are no conflicts in the field. That is to say that no two devices have the same address. I2C is a serial communication protocol. You only need two bus lines to implement it, the serial data line, SDA, and serial clock line, or SCL. This is a big advantage of I2C compared to other protocols like SPI, which need 4 wires and an additional chip select line for each additional SPI device on the bus. In I2C, each device on the bus has a unique address that is hardwired into the device itself. Some devices allow you to write to a register to choose between a few addresses. This is useful if you intend to use multiple of these devices on the same I2C bus. The I2C bus supports more than one master, although it should be checked if the devices that are on the bus also support this arrangement. It is a bidirectional bus, which means data can flow both ways, that is from master to slave and from slave to master. With the 10-bit addressing scheme, you can connect roughly 1,000 devices on the bus. But the limitation here is not how many combinations of addresses are possible. It is the capacitance of the bus that should allow this arrangement. We will look further into capacitance issues in just a few moments. There are 5 modes that I2C can operate in. The standard mode gets you a speed of 100 kilobits per second. The fast mode gets you 400 kilobits per second. The fast mode plus gets you 1 megabit per second. The high-speed mode gets you 3.4 megabits per second. And the ultra-fast mode gets you 5 megabits per second. To give you some perspective on this, internet communication on a Cat5 Ethernet cable at your home can get you up to 100 megabits per second. So I2C might not be the fastest communication interface out there, but it is widely used in inter-IC communication, since it only requires 2 bus lines to implement. Not all devices will support all the different I2C modes. You will need to check the datasheets of the devices to see which of these modes they support. You will see that a majority of the I2C devices that we encounter in our projects support the standard, which is the 100 kilobits per second, and the fast mode, which is the 400 kilobits per second.